So I just decided to whack it out with something that looked about right. And it is about right, and it works about right. Should have done it better though. Hi, it's Todd from Todd's Workshop and Todd Cutler here, and today I'm back with the Catapulta again. But it's going to be kind of slow TV, this one, because I'm going to talk you through every aspect of it, every little element that I can think of that I think either I'm interested in or you might be interested in. But the thing is, I originally worked with this guy, Alan Wilkins, 10 years ago now. Now, Alan Wilkins is a man who knows a vast amount about these machines, and him and another guy called Len Morgan all contributed to put together Marsden's Greek and Roman artillery. And this is, well, it's a two-part series, fantastic books. This is the second one, Historical Development. And the thing about this book is it lists on tables every detail, dimension you could ever want for reproducing these machines. Well, almost. There is a danger here that I'll just go on forever and ever. So I'm going to try and keep it to the really important bits, so there's going to be stuff that I miss out. But fundamentally, the data in this book, the data tables in this book, were taken from the works of Philon and Vitruvius. Both of those guys were a couple of hundred years apart, but they were also incomplete. But between the two of them, you can pretty well extrapolate what the dimensions of every element is. And that is what they did for this book. So you're all going to rush out and go and buy this book, aren't you? Well, no, you're not. Because unfortunately it's out of print, and if you can find copies of it, it is viciously expensive. So I'm going to share with you everything that I can out of this book that I remember. However, this was 10 years ago I did this, and it does mean I'm going to tell you, what I know, or at least what I think I know, but probably some of my detail might be a little bit wrong, and without reading the whole book again to make a 20-minute film, I can't give you the exact. But this is going to be a good tour of this machine and essentially the contents of this book, which is what I used to make this. It is the engineering that really fascinated me about these machines, because they do something very, very clever. And that is that they scale their engineering. And for a dynamic device, a machine that moves and moves quickly with big stored energies in it, that scaling is really, really unusual. Engineering doesn't scale. It's just a phrase that engineers know. But the thing is, you can build this 1/3 size, shoot 660 yards. 3 times the size as this one is, 660 yards. And the bolt, 3 times as big, so on. It's an extraordinary feat. And all of this engineering starts with the hole diameter here. Now, I forget exactly, but I think that it's 1/8 of the length of the bolt that you want to shoot. So if you've got a 1-span machine, it would be 1/8 of that. If it's a 3-span machine, it's 1/8 of that. And that's what we have here. Now, every other timber from here, every timber on the machine is now related to the size of that hole. And what that means is, in sort of field repair terms, you're in the wilds of Germany, for instance, you haven't got a lot of legionnaires who are trained in siege artillery itself and manufacturing the items. But the guy who does know can give them a stick and he goes, I want a timber that is 1 hole wide, 1 hole high, 14 holes long. And it becomes the new stock of a machine. And that level of simplicity and genius is just fantastic. And then on top of that, for the things to shoot brilliantly efficiently, extraordinarily, 660 yards for anybody who's involved with bows is one heck of a long way. We all know that. So really, these things just grasp me at the first moment. Now, the engines of this machine are the torsion bundles, the springs here. And these are ropes that are incredibly tight already before we've even put any turn on them. And I'm going to show you how to do that later on. But these ropes here originally were made of horsehair. And so what happens is they are stretched as they go in. There's a lever and they're clipped and they're stretched into place. And in fact, that the Romans used to ask that the people who loaded up the ropes on these machines were musical, because you pull it to a certain tightness and you pluck it and you get a note. And each time you pull it to the same tightness and you pluck it and you get the same note. And that way you get really efficient bundles. It also means if you pluck to the same note, you can get the same pre-tension on each side, which makes life a bit easier. So horsehair rope is purchasable these days, but it is vastly expensive. So I've gone for a pre-stretched polyester here. And it looks like a natural rope. It's not actually, it is a plastic. Sorry, everybody. But that gives a really, really good result. And that's what I was recommended to use. You don't want a 0 stretch fibre, because then there's no spring in the fibre itself. What you're looking for is something which has a tiny bit, but you can really control it. What you want on any projectile device is a long power stroke. The longer the power stroke, the more power you're going to get out of the machine and into the projectile. If these arms were straight, and they did make them straight in the early days, if these arms were straight, the string ends up stopping about here, because otherwise these arms are going to foul on the frame. Now what that means is that you are short of 6 inches, 15 centimetres of power stroke that you could have if you curved the arms. And they worked this out, I think about 100 BC, something like that, and they started to curve the arms. And they'd glue them up and laminate them just as I've done there. I've actually used a boat builder's glue called Resorcinol, and it is incredibly strong. People who laminate longbows as well, they often use it. And it's fantastic for this. So that allows me to have the string all the way up to the end. The power stroke is as long as it can possibly be. These machines went through an awful lot of development from when they first left the Greeks and then they came into the hands of the Romans. The headstocks here were all of wood. But of course, if they're all of wood, it limits in a way the power that you can put into it, because sooner or later the wood starts to break. Well, what they again learnt is that you can start to plate the wood. So all of this steel plating here is not a confection of mine, it is what they started to do. And so you have all of the sides plated here, and then effectively a top cap and a bottom cap going on, and that's all sandwiched together using the bronze washers at the top and these bundles here. So the whole lot is pulled in. And what that means is that these are now going to be on really, really strong supports for the whole framework. But perhaps not strong enough, because look at this, we do have some repair work to do. Now I have a bit of a problem here, and I'm not sure how much you can see, but this steel plating here, it's flat, 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 exactly as you would expect. It's really strong here in this box section at the front. But as it comes here at the back, around this cutout, it's starting to buckle out. And if it's starting to buckle out, that means that in fact, this whole framework is bending in a little bit like that, which is of course massively disturbing. I don't know how many tons of pressure there are pulling in here when I wind it up, but it will be considerable, I can tell you that. I'm not saying several tons out of a joke. That really is the case. And that's causing this to buckle. Now, I can go back in here and I can put another couple of rivets through, and I'll do that. But of course it leaves you with the question, why was it buckling? Now, one of two things. Either the whole thing is in danger of just collapsing and breaking, which I really don't want to happen. But actually, if it does happen, I don't think that would be a catastrophic failure in the engineering term, that it would just explode and bits go everywhere and it takes my head off. I don't think it would do that. I think it would just fold and collapse on itself. Depressing, upsetting, but not dangerous. But I think the reason it's happened is I made a stupid mistake when I made this machine 10 years ago. I made it out of green wood. What do I mean by green wood? Well, it was wet, it was fresh, it was new. And you do that with oak because it makes it easy to work. And there's good reasons for it. But of course it then changes shape. And I think that this may have shrunk a bit, and the steel of course hasn't. And that's where that buckling has come from. But I can't know. I can't know. So I'm going to go in and repair that before we wind it up. But come and have a look at this back end and you'll see what I mean by the whole movement of the oak. So this is the stock of the machine, and you can see that the whole thing twists as it comes down. I'd rather it wasn't like that, I really would, but it is like that. I don't think it matters very much. I don't think it matters structurally, I don't think it matters accuracy or performance-wise. It's just, you know, not what I want it to be. But it does that because all of the wood moved. And yeah, rookie's mistake maybe, because I don't do that much heavy woodwork like this. If I did it again, I'd do it in seasoned. So those torsion bundles, when they're actually put into the machine, they are pre-tensioned massively. Like I said, you should be able to pluck them and get a musical note off them. Now, of course, anything like that, you know, if somebody put a knife on one of those things, it would just come apart. So, of course, massively vulnerable to any incoming projectile. So they put an armoured plate on the front. So actually we have a beautiful little repoussé thing here, but behind it is steel, iron. So that iron plate protects the machine. But then over the front, if you've got that plate, you know, the Romans were the kings of decoration and making things look cool. So I've got a god here spitting some bolts, and again, I'm pretty sure I took that off an original piece or something very similar to it. Now the hole here, I might have made a little bit small because I'm fletching these bolts here. But there are some which came from a Roman camp called Dura Europus, which was in Syria. And that didn't survive very long. They built it and then quite rapidly it was taken over. But the sands came in and buried it. And that means there are some fantastic finds there in really good preservation. Some of those are bolts for these. And they're the only ones, I think, where we have the whole shaft and everything. And they're really quite interesting. They are different to this. I have shortcut it. but they waste down, so they get thinner and they widen out quite a lot. I think they've got 3 wooden fletchings on them, as far as I remember, and they're actually taller than they are wide at the back. Really quite interesting. Complicated to make, which is why I didn't bother for this. But you wouldn't get those wooden fletch bolts through a hole that size. So it is fair to say that I have taken some liberties with this machine, because I was more interested in the technology and how it worked than actually the precise historical nature of it. That was 10 years ago. Now if I did it, I think I would actually put that little bit of extra time into trying to nail every detail right. And one of the things that I definitely did get wrong was the stand. It's well defined in this book here, and have a look at this picture. But it shows you quite clearly what it should be. Mine is not a million miles from that. But again, I had to make the stand in a bit of a hurry for some telly programme, so I just decided to whack it out with something that looked about right. And it is about right, and it works about right. Should have done it better though. Now the trigger system is very, very similar on all manner of these devices, whether it is a catapulta, a ballista, a gastrophetes, which is an earlier Greek invention. They're all very similar. And you have a main stock here with either a dovetail or a T-shaped groove out of the top. And in that is this thin wooden slider. Now that slider, you might think, is structurally part of the whole trigger system. It's not really, it just dangles off the front. And the bolt sits on it, it rests on it. It's no more than that. So it's actually a fairly flimsy bit of wood that just goes up and down. It is riveted to the whole trigger block here, and that is what is attached to the winch. So it is, in fact, it is just getting dragged along by the trigger block. No significant forces going through it. So the winch winds that back, and this system here is absolutely correct. It's absolutely fine for a Roman catapulta of this kind of period. But they also had a fantastic development, which were 2 ladder racks that went up the side. And then you have the winch system at the back here, and that is pulling this trigger block. So there's an awful lot of force associated between these. But the slider itself doesn't really come into much of it. But this is a very simple windlass system. The Greeks had it, and this whole system just went through the Middle Ages, even probably into the early modern times now. But the Romans, of course, being Romans, got really excited about developing new things. So although this is correct for this period of machine, it's fine. There was also another system they had where they had these 2 racks of teeth that slid up and down on the side. 2 levers that cranked it. Faster, more compact, more contained, no ropes to dangle about, but a lot more complicated to make. So I was stuck on the easy end of things for this. And then the trigger itself, totally ancient technology. Even by this period, it's at least 500 or 600 years old. And it is just brilliant. It seems to me like a trigger system that shouldn't have fallen out of use, but it did. Maybe it did sort of fall down with the Romans when the Western Roman Empire fell. I don't know. I don't know if it carried on in Byzantium, in the Eastern. But it's a brilliant system. And all you've got is a wedge here that holds that. Now, if you have a slight slope on that wedge, it won't spit it out. It won't be prone to a hair trigger. But a little bit of a wedge means that you can keep it moving, and it just opens slightly. It just makes for a really, really nice system. Very easy to retune if it gets a bit stiff or anything else. If it gets a bit grooved, you can repolish it up. Just a beautiful system, and it allows you to release easily very, very high loads, because this will produce high loads. I don't know how high, but it'll be big. We'll try and get a scale on it. Yeah, what? Yeah, right. Let's put a load scale on it. Now, to make this machine manoeuvrable, it needs to pivot more or less on its centre of gravity, but in fact, it's come just to one side. So what we can do now is it just rests back here. Nice heavy winch system just allows it to rest, and then when I want to shoot, I can lift up, and there's no problem at all. I can just move it very easily. And that allows me to position high, long shots, close, low, whatever it may be. But it's all done without very much effort. Now, before we start to do that repair on the sides here and then start to tension up, I'll just take you, just slowly, looking at the different elements, piece by piece, so you can get a good idea for how it all relates to each other. I'm going to drill through now, here and here, and put bolts in. Rather obviously, I don't want to go too deep because right behind that is our rope bundle, so I've got to be careful. That'll do. Just trying to clamp it down. Not even sure I should do this actually from a structural point of view, but either way, no, I'm not actually moving it. So I'm just going to bolt it back up, and that way it'll just stop it getting any worse. The thing is, these dome-headed bolts aren't going to look too out of place. Got square nuts on the inside. I riveted the original structure, but with a little bit of age, this will look just fine. Good. So I'm going to repeat on the other side, and then we're ready to put some tension on it. I've put a couple of extra bolts on each side there around that buckle. So now I've got to put the arms back where we were, and then I'll put a weighing scale on it. So this is all kind of guesswork at the moment. It's quite interesting because you need to balance the tension that you put on to each side, because otherwise the arms themselves don't stay square to the stock, so they won't do that. They'll be off at one side. So actually you've got to balance it. At the moment the arms are completely on tilt, and in fact this is showing a problem that we're going to have. My lever is long. I can put a lot of power on it. Jenny can't hold it. So we can do a little bit now, and we'll see where we're going to go to, but then we have to take the headstock off the frame and do all of this tensioning off the machine. So we've got another frame for that. I'll show you that in a minute. I have a crane scale here, basically a set of scales that you put on a crane. That's pretty obvious, isn't it? But the reason that I've got them is that they go up to a ton in draw weight. So I use these for measuring my crossbows actually, but it will work just fine for this as well. So we're just going to put it into position, and we'll get some feeling. I'm not going to pull this back very far, 10 inches or something, and we'll get a feeling for how powerful it is. And then I will try and increase the weight as much as I can using that long lever, and we'll just have another look, just get a feel for it. So all I'm going to do now is just tie that scale onto the trigger. It does make it very, very easy, this sort of trigger system. So we're turning the scales on. I'm just going to put a mark here. I'm going to do one, let's say 10 inches, 25 centimetres further down the stock. And we're going to have a look at what weight that is drawing at that point. And here we are. So, a not very impressive 45 kilos. So that's about 100 pounds in draw weight. And that's what? Over 8 inches, 25 centimetres. Let's go back a little bit more. See how we go with that. So from our original mark, let's go back 18 inches, which is 46 centimetres. So it's definitely getting harder to do at this end. But probably not massive numbers still. Okay, so that's 170, 180 pounds. So 180 pounds on an 18-inch draw length. Well, that's pretty significant, but it's not going to shoot 660 yards. What I'm going to do now is try and increase the power of this as much as I can with the headstock in situ. So I've got my trusty spanner. I'm going to wind those torsion bundles up again. It might get a bit comedy, but probably it will increase it, but not by that much, I'm thinking. Okay, ready? Okay, oh, nice. Again, so I'm now going to try and put the bottom bar, the bottom bundle, in about the same orientation as the top part of the bundle. This might be a bit difficult. That's my lot. Ready? Okay. So that you can see is the problem. I've done as much as I possibly can. Let's get it back with the scales again, and then we'll have to get the headstock off and do it separate. So immediately you can feel it's harder actually. But that is the biggest extent that I can give it with the headstock mounted on the frame. 121, there we are. Just going to pull the headstock off now and then get it onto our framework. Okay. So that's the end of the first part of our film. Basically walking around the Catapulta, explaining some of my choices, some of the things you need to watch out for. And now we're going to tension it up and then we're going to shoot. But that's the next part.